March 2022, Arabian Sea. An Indian Navy destroyer fires what looks like a telephone pole with a rocket motor attached, 9 meters long, over 3 tons at launch, moving at speeds that make physics scream in protest. This isn't a ballistic missile arcing into space. This isn't a torpedo hugging the ocean floor. This is a cruise missile flying 50 feet above the waves at Mach 2.8, nearly 2,000 miles per hour, at sea level, where air is thick, where aerodynamic heating should melt control surfaces, where shock waves should rip the airframe apart. And somehow, this weapon maintains controlled flight, executes terminal maneuvers, and impacts targets with precision that shouldn't be possible at those speeds. This is the BrahMos, a missile named after 2 rivers, the Brahmaputra in India and the Moskva in Russia, the fastest operational cruise missile ever built. And the reason it's deadly has nothing to do with the warhead. It's about what happens when defenders have 28 seconds from detection to impact, when decision cycles collapse to time frames where human reaction is physically impossible, when the laws of physics that should make this weapon impossible instead make it unstoppable. Let me show you why faster changes everything, how supersonic sea skimming breaks defensive mathematics, and why the wildest solution to anti-ship warfare is a missile that flies so fast it shouldn't work but does anyway. The problem is time. Traditional subsonic cruise missiles travel at Mach 0.8 to 0.9. That's roughly 600 miles per hour, fast for an aircraft, slow for modern ship defense. A subsonic missile detected at 20 miles gives defenders approximately 2 minutes from detection to impact. 2 minutes to track the threat, calculate intercept solutions, launch defensive missiles, and execute engagement. 2 minutes is tight but manageable. Aegis systems are designed for exactly this scenario. Radar detects the threat. Computers calculate trajectory, standard missiles launch. The intercept happens at 10 to 15 miles, well before the threat reaches point defense range. That timeline assumes the attacker gives you 2 minutes. BrahMos doesn't. The missile flies at Mach 2.8 at sea level. That's 2,100 miles per hour. Detected at 20 miles, it impacts in 34 seconds, not minutes, seconds, and detection doesn't happen at 20 miles. The missile flies at 10 to 15 meters altitude, 30 to 50 feet above the waves. Radar horizon at that altitude is roughly 12 to 15 miles for ship-based radar systems. BrahMos appears on radar at 12 miles. Impact occurs 20 seconds later, 20 seconds from detection to impact. That's not an engagement timeline. That's barely enough time to sound alarms. And here's what makes it exponentially worse. The missile doesn't just fly straight, it executes S maneuvers in terminal phase, weaving laterally to defeat point defenses at Mach 2.8, pulling multiple Gs, maintaining trajectory toward a target. The aerodynamics shouldn't allow that. Control surfaces operating in supersonic airflow experience massive forces. The slightest input creates violent responses. Overcorrect by a degree, and the missile tumbles. BrahMos pulls sustained 10 G turns without losing guidance or breaking apart. The engineering required to make a 3-ton missile maneuver like a fighter jet at nearly 3 times the speed of sound is borderline insane. But it works, and that's what makes it deadly. The development history reveals why the missile is so extreme. India and Russia formed BrahMos Aerospace in 1998 as a joint venture. Russia provided the P-800 Onyx platform, a proven supersonic anti-ship missile design. India provided systems integration, guidance, and production capability. The goal was creating an exportable supersonic cruise missile that didn't violate missile technology control regime restrictions, limiting range to 300 kilometers. Fast, maneuverable, but range limited to avoid proliferation concerns. The result exceeded expectations. The missile achieved speeds approaching Mach 3, terminal maneuverability that defeats most point defenses, accuracy measured in meters, and reliability proven through hundreds of test launches. The first naval version entered Indian Navy service in 2005 aboard destroyers and frigates. Since then, BrahMos has proliferated across surface ships, submarines, aircraft, and mobile ground launchers. It's not just a naval missile. It's a multi-domain weapon that happens to excel at killing ships, because ships are large, slow targets compared to maneuvering aircraft, and BrahMos arrives before they can effectively respond. The propulsion is a two-stage system. A solid fuel booster accelerates the missile to supersonic speed within seconds of launch. Then a liquid-fueled ramjet sustains Mach 2.8 3.0 cruise throughout the flight profile. Ramjets are simple in concept. Ram air into a combustion chamber, add fuel, ignite, and exhaust provides thrust. No compressor stages like turbojets. No complex moving parts. Just inlet, combustion, exhaust. But ramjets only work at supersonic speeds. Below Mach 1, they don't generate thrust. That's why the solid booster exists, to accelerate the missile to speeds where the ramjet becomes effective. Once the ramjet ignites, the missile maintains speed through continuous fuel burn. Range is limited by fuel capacity, not propulsion efficiency. The missile flies until fuel exhaustion, then ballistically impacts within seconds. The fuel is a liquid hydrocarbon mixture stored in internal tanks. The missile carries approximately 1,500 kilograms of propellant, enabling ranges of 290 to 400 kilometers depending on flight profile. Extended range variants under development claim 450-500 kilometers. That range is substantial. A destroyer positioned 250 kilometers offshore can strike targets deep inland or engage enemy ships well beyond their weapon ranges. The missile's speed means even distant targets are reached in minutes, not hours. But range is secondary to speed. The real advantage is compression of defensive timelines to the point where even automated systems struggle to respond effectively. The guidance system combines inertial navigation with active radar homing. After launch, the missile flies a pre-programmed route toward the target area using GPS and inertial guidance. As it approaches, an active radar seeker activates, detecting targets and guiding the missile through terminal phase. The seeker operates in a frequency band optimized for detecting ships against ocean clutter. It can discriminate between multiple targets, selecting high-value threats based on radar cross-section and positional data. And it does this while traveling at Mach 2.8. The computational challenge is enormous. The missile covers 1,000 meters per second. Sensor data updates hundreds of times per second. Flight control algorithms make continuous micro-adjustments to maintain trajectory, all while aerodynamic forces try to rip control surfaces off and shock waves buffet the airframe. The fact that it works reliably is testament to sophisticated engineering and extensive testing. The warhead is a 200 to 300 kilogram semi-armor piercing high explosive charge. Not the largest warhead by naval missile standards, but it doesn't need to be. When something weighing 3 tons impacts at Mach 2.8, the kinetic energy alone is devastating. The warhead adds to that kinetic impact, but even without detonation, the physical collision would cause catastrophic damage to any ship. Naval architects design ships to withstand 1-point impacts from warheads. They don't design for 3-ton projectiles traveling at 2,100 miles per hour. The structural stresses exceed design parameters. Hulls rupture, bulkheads fail. Ships don't just get damaged, they get torn open, and the warhead detonates inside the ship after penetrating the hull, maximizing internal damage to vital systems, magazines, and engineering spaces. The no combination of kinetic impact and explosive detonation is more destructive than either alone. The tactical employment is straightforward. Target identified through reconnaissance or electronic surveillance. Firing solution calculated, missile launches, flies low to avoid early detection, activates seeker in terminal phase, executes S maneuvers while closing, impacts before effective defense can be mounted. Against isolated ships with limited defenses, BrahMos is nearly unstoppable. Against well-defended carrier groups with layered air defense, it's still extremely challenging to counter. The defensive problem is geometric and temporal. To intercept BrahMos, defenders must detect it early, calculate intercept solutions instantly, and launch defensive missiles with enough lead time to reach intercept point before BrahMos arrives. Detection at 12 miles. BrahMos arrives in 20 seconds. A standard missile needs 8 to 12 seconds to launch, accelerate, and reach intercept point 5 to 8 miles from the ship. That leaves 8 to 12 seconds for human decision-making or automated engagement authority. 12 seconds is insufficient for human decision cycles. Humans need time to assess the threat, evaluate options, authorize engagement. By the time that happens, BrahMos is inside point defense range, where close-in weapon systems have maybe 3 to 5 seconds to engage. That's why modern Aegis systems have automated engagement modes. The computer detects the threat, calculates it as hostile based on speed and trajectory, and fires interceptors without human authorization. The decision cycle collapses from minutes to milliseconds. But even automated systems struggle against BrahMos. The missile's terminal maneuvers create targeting solutions that change faster than fire control systems update. Interceptors calculate where the target will be, but BrahMos isn't there because it maneuvered. The interceptor misses. Another launches. Maybe it hits, maybe it doesn't. Meanwhile, 20 seconds have elapsed and BrahMos is already impacting. The probability of successful interception drops dramatically compared to subsonic threats. Some estimates suggest even advanced systems like Aegis have 40-60% interception probability against single BrahMos missiles compared to 85-95% against subsonic targets. And adversaries don't fire one BrahMos, they fire salvos. 4 missiles approaching simultaneously from different vectors. The defenders must intercept all 4. Miss one and it impacts. The mathematics favor the attacker. The international adoption reflects confidence in the weapon. India operates BrahMos across all services. The Philippines became the first export customer in 2022, procuring shore-based variants for coastal defense. Indonesia, Vietnam, and several other nations are evaluating purchases. The missile is expensive, approximately $2.5 to $3 million per unit. That's significantly more than subsonic alternatives like Harpoon at $1.4 million, but the capability difference justifies the premium. You're paying for speed that compresses defensive reaction time to seconds. You're paying for terminal maneuverability that defeats point defenses. You're paying for a weapon that forces adversaries to invest billions in defensive systems that still struggle to intercept reliably. From a cost exchange perspective, spending $3 million to threaten a $2 billion destroyer or $13 billion carrier is extraordinary value. The target must expend multiple interceptors costing $2 to $4 million each, attempting to stop a single BrahMos. If 4 BrahMos attack simultaneously, the defender fires 8 to 12 interceptors. That's $20 to $48 million in defensive missiles against $12 million in offensive weapons. And if even 1 BrahMos penetrates, the ship is mission killed or sunk. The economic calculation favors the attacker. The physics of supersonic sea skimming are genuinely wild. At Mach 2.8, air resistance is enormous. Drag forces are proportional to the square of velocity. Doubling speed quadruples drag. At nearly 3 times the speed of sound, drag forces are crushing. The missile compensates through sheer thrust. The ramjet burns fuel continuously, generating constant forward thrust that overcomes drag. Fuel consumption is high. The missile burns through its propellant in 3 to 5 minutes depending on flight profile. But those 3 to 5 minutes are enough. The missile reaches 300-kilometer range before fuel exhaustion. And once the ramjet flames out, momentum carries the missile forward for several more seconds before aerodynamic drag decelerates it significantly. The timing is calculated precisely. Fuel exhaustion should occur just seconds before impact, ensuring the missile maintains maximum speed through terminal phase. If fuel runs out too early, drag slows the missile and gives defenders more time. If fuel is conserved unnecessarily, range capability is wasted. Flight profiles are optimized through testing, hundreds of launches across various atmospheric conditions, target ranges, and engagement scenarios. Engineers measure actual performance and refine fuel consumption algorithms to maximize speed-range product. The result is a missile that maintains Mach 2.8 until the final moments, then impacts at Mach 2.5, 2.6 after brief fuel exhaustion, still supersonic, still devastating, still barely interceptable, the heating effects are severe. At Mach 2.8, aerodynamic friction heats the airframe to temperatures exceeding 500 degrees Celsius on leading edges and control surfaces. Standard aluminum alloys would soften or melt. BrahMos uses specialized materials and thermal management, titanium alloys on high heat areas, ablative coatings that char and dissipate heat, internal cooling passages that route fuel past hot sections, using the fuel as a heat sink before burning it in the ramjet. The nose cone endures the most extreme heating. It's not just leading the supersonic airflow, it houses the radar seeker that must remain functional despite external temperatures that would fry conventional electronics. Active cooling and insulation protect the seeker. The radar operates behind a heat-resistant radome designed to remain transparent to radio frequencies while withstanding thermal stress. Engineering that into a structure that survives repeated 10G maneuvers is remarkable. The control surfaces face similar challenges. They deflect into supersonic airflow, experiencing massive aerodynamic loads and heating. The actuators moving those surfaces must generate enough force to overcome airflow resistance while maintaining precision measured in fractions of a degree. Hydraulic actuators with high-pressure systems provide the force needed. Reinforced control surfaces with heat-resistant construction survive the thermal environment, and flight control algorithms compensate for aerodynamic effects that would cause catastrophic instability if not managed precisely. That combination of systems working simultaneously at Mach 2.8 while pulling 10G turns is why BrahMos is wild. Each individual system pushes physical limits. Together, they achieve performance that shouldn't be possible, but is. The strategic implications extend beyond ship killing. BrahMos creates area denial effects. Naval forces know that operating within 300 kilometers of BrahMos-equipped platforms is extremely high risk. Carrier groups maintain greater standoff distances. Amphibious operations are constrained by shore-based BrahMos batteries. Naval blockades become exponentially more difficult when the blockaded nation can strike blockading ships from hundreds of kilometers away. That strategic effect exists whether BrahMos fires or not. The threat alone shapes operational planning. Ships route around known BrahMos deployments. Aircraft carrier operations remain farther offshore. Naval presence is reduced in contested areas. China faces this with India. The Himalayan border is land-based, but both nations have substantial naval forces. Indian ships armed with BrahMos threaten Chinese naval operations in the Indian Ocean. Chinese ships face weapons they struggle to intercept reliably. Similarly, Pakistan operates near Indian waters where BrahMos-armed vessels create significant threat. Philippine BrahMos batteries deployed to islands in the South China Sea threaten Chinese ships operating in disputed waters. The weapon creates tactical and strategic effects far beyond its technical specifications. It changes how navies plan operations, how they position forces, how they calculate risk. The testing is extensive and ongoing. Hundreds of launches across all variants, ship-launched, submarine-launched, air-launched, ground-launched. Success rates exceed 95%, demonstrating reliability across platforms and conditions. Recent tests involved salvo launches simulating coordinated attacks, multiple missiles launched simultaneously, programmed to arrive from different directions within seconds of each other. The coordinated timing and distributed approach maximize probability of penetrating defenses. Other tests focused on extreme range, with extended range variants achieving 450-kilometer shots, and air-launched versions tested from Su-30 fighters demonstrating BrahMos can be delivered by aircraft, dramatically extending launch platforms. The future variants are even more extreme. BrahMos 2 is under development with projected speeds of Mach 5 to 7. That's hypersonic, adding complexity to defensive problems already severe at Mach 2.8. Hypersonic BrahMos would reduce defensive reaction time to 10 seconds or less. At Mach 7, detected at 12 miles means impact in 9 seconds. That's not defensible by current systems. That's impact before defenses can respond. Whether hypersonic variants achieve operational status remains uncertain. Hypersonic cruise missiles face enormous technical challenges, but even current BrahMos is extreme enough that hypersonic versions seem like inevitable. Evolution, rather than fantasy. The wildest naval missile ever built isn't wild because it does something unique. Plenty of missiles fly fast. Many are maneuverable. Some carry larger warheads. BrahMos is wild because it does everything at speeds that make doing everything simultaneously seem impossible. Supersonic cruise at sea level, terminal maneuvers while supersonic, precision guidance against maneuvering targets, reliability across hundreds of launches. Each capability individually is difficult. Together they're wild, 9 meters long, 3 tons, Mach 2.8, and defensive timelines measured in seconds instead of minutes. Ships facing BrahMos don't have time to think, they have time to react. And reaction without thought is hope, not strategy. That's why it's deadly, not the warhead, the time, or rather the lack of it. Because when missiles arrive faster than humans can decide and barely slower than computers can calculate, defense stops being about capability and becomes about mathematics. And the mathematics say 20 seconds isn't enough. Not against a target pulling 10 Gs while traveling 1,000 meters per second. The wildest missile isn't the biggest or the smartest, it's the fastest that still works. And BrahMos works at speeds that break everything else. That's wild. That's deadly. And that's why navies fear it more than weapons twice its size, traveling half its speed. Because slow gives you options, fast gives you impact, and Mach 2.8 gives you 20 seconds to realize you're already dead.